Welcome everyone to our interesting seminar. Okay, we first of all thank you a lot, Professor Popovski, for accepting the invitation for our seminar. Let me give some information about Professor Popovski before he starts. I'm sure all of you already know Professor Popovski. He is outstanding researcher within the wireless communication community. He is an IEEE fellow and professor at Aalborg University. He has participated in so many activities at IEEE and within technical committees. He is a member at large at the Board of Governors of the IEEE ComSoc. Okay, and he received many awards at Denmark and worldwide, and from IEEE, both General IEEE and ComSoc. The seminar for today has this topic, wireless connectivity beyond 5G. Okay, talking about spectrum, so a take on spectrum, time, space, and blockchain. So an interesting topic, Professor Popovski. So with that said, thank you again for accepting the invitation, and we are honored to have you here. So please, the floor is yours. Professor Popovski, we don't hear you.
Oh, no, I was muted. So
okay,
thank you very much for, yes, that should be okay now. Thank you very much for the invitation and for the kind introduction. It's my pleasure to present to this community. So I'm going to start. Actually, the talk has a couple of different aspects. So I will touch upon very different things, but I have tried to connect the multiple research topic we are doing into a single whole. So I hope I'm going to succeed in that. So I'm going to start with discussion on the connectivity types, which were defined with 5G, and now as we are moving towards the next generation to see what are the challenges in defining these connectivity types. Then I'm going to speak about sharing of the spectrum while guaranteeing heterogeneous performance guarantees, which we call spectrum slicing, inspired by the network slicing at the higher layers. And then I'm going to cover connectivity and timing, and connectivity and new spatial properties, which are appearing in wireless systems. And finally, we are going to switch gears and go to distributed ledgers and blockchain and see how and why they are important for IoT and what is their impact on the communication aspects of IoT. So let's start with the connectivity types. So the connectivity ecosystem today is quite complex because we have human to human, human to machine, machine to machine connections, and many of them with very different requirements, very varying rates. Some of them require very low latency. Some of them require many devices to be connected, and so on. So this type of connection were existing for many years, but finally the main innovation, I think, of 5G is to deal with this complexity by defining three types of connectivity, which you're all familiar with: is enhanced mobile broadband, massive machine type communication, and ultra reliable low latency communication. And then the main innovation of 5G is probably to offer a platform that is going to flexibly support all these heterogeneous services. So we're having a platform that can adapt and satisfy these very diverse requirements. So we should, if we distill the requirements of these services, then we say that EMBB is kind of acceleration of 4G, where we look at large payloads, large data transmission, and we want to maximize rate and throughput, while the reliability for transmissions is moderate. On the other hand, we have massive machine type communication, where we have fixed low rate, many devices connected. This fixed low rate is, of course, an approximation, but we are saying that there are many devices requiring relatively low rate. Most of the time, this rate is fixed. And the main challenge is to find what is the active subset of devices which wants to send at a given moment. So we would like to maximize the activation rate, the arrival rate of the packets at this population of devices. Finally, is the new mode, I would say, that is brought by 5G, is the ultra reliable low latency communication, where we look into intermittent transmissions, but from much smaller set of devices. So here the objective is to offer very high reliability, for example, 10 to the minus 5 per packet transmission, while being localized in time. And then we should not think about this services as every device is going to just belong to one type of service. In principle, we're going to have composite services where we are combining the properties of these three different types of connectivity, for example, to satisfy something in industrial connectivity, to satisfy a requirement in virtual reality, where we are having, for example, a low latency command, which is invoking high data transmission, or vehicle-to-vehicle communication. So we should think probably about this connectivity space as being spanned by these three services, by these three dimensions. But of course, the question is, how are we sure that these are the three right dimensions? So I'm going to talk a little bit about that. So let's look into the high reliability and low latency. So the 5G community has opted to couple the ultra reliability and low latency into URLC. And for a long time, the requirement that was defining URLC was error rate of 10 to the minus 5 under this proverbial 1 millisecond. So the main motivation for this is that we would like to slice a small part, predictable part of the latency budget of 1 millisecond, and then leave the other part of the latency budget to whatever other operation we have, for example, computation, compression, and so on. So in principle, information theory guarantees perfect reliability. So if you look at Shannon's theorems, he tells when it is possible to communicate with a probability of error that converges to 0. However, this is happening provided that the sender knows the channel statistics and is capable to select the coding rate to be below the channel capacity. So if we are communicating below the channel capacity, asymptotically, we can achieve probability of error 0, so perfect reliability. And of course, in Shannon's case, the time does not play a role because we are considering asymptotically many transmission uses of the channel, so we have potentially infinite latency. So the point is that it's of course reasonable to put latency requirement and resource constraint in order to see what can be achieved. The question is whether this should be always set to, let's say, 1 millisecond or some very low value. So in an early 5G proposal, almost 10 years ago, we had proposal for ultra reliable communication over a long term, which is where the latency is larger than 10 milliseconds, and ultra reliable communication over a short term where the latency is less than 10 milliseconds. So we wanted to divide the latency into two classes, not to insist that we always slice this very small piece of the latency budget. So, and this was for some reason not accepted at that time, but we can see that now there is a revision within 5GPP, within 3GPP, sorry. And so in the new 5G requirements, we can see that there is a gradation of different types of latency in these low latency services. So there are at least 3 cases for longer term ultra reliable connectivity. So for example, we have the case of mobile health or remote monitoring, where the latency is not very important, but it's important to keep the connection all the time alive. Then we have disaster and rescue, and where a couple of minutes would not make a difference, but that message should get through. And also the smart grid, where, for example, if the grid is running with 50 hertz, then the important timing is of 20 milliseconds. So everything kind of happens with cycles of 20 milliseconds within which we should have to satisfy certain communication requirements. And even if you look into what happens in industrial connectivity, with the 5G Alliance for Industrial Connectivity defining 3 types of real time. One is non-real time with seconds. Second is soft real time within a second, and the third one is hard real time within milliseconds or even microseconds. So this brings me to the fact that there might not be 3 but 4 different dimensions which we need to use to define connectivity types. So one is reliability, second is latency, third one is data rate, and the fourth one is massiveness. So if we take tactile robotics, for example, robots which are controlled with remotely by human operators. Then we have a high reliability, low latency, relatively low data rate, and relatively low massiveness. So here we have kind of URLC, which is the one is defined in 5G. But then we have health monitors, where we have high reliability, many devices, but not very low latency and not very high data rate. And we also have augmented reality, where it's a little bit opposite. We have high data rate, low latency, not very high reliability because they're not mission critical. And then massiveness might not be also very high. So the number of involved devices might not be very high. So what is the challenge in this sense? So let's say that with 5G, we have defined these three types of connection. So if we look forward towards the next generation, let's call it 6G or whatever we call it, what is the challenge into dealing with this type of connectivity? So I think we need to have an improved understanding of the connection ecosystem, because with 5G, we defined these 3 dimensions. Now with what I have presented, we are kind of revising the 3 dimensions going towards 4, but there is more to it. So what we can do is map the population of connections to these 4 generic connectivity types. But the large unknown space of research is characterization of the composite connections. So for example, we have low latency traffic arrivals from the same device correlated with broadband requests. So this correlation among the arrivals, so the probabilistic and the causality among different traffic types, is creating an opportunity for efficient resource allocation. So we have to find a systematic way to characterize connections which are not relying only on one type of generic service, but they are multiplexing different types of this service. And the question is, what is the best statistical characterization of it? Because each of these is going to require different rate, is going to have different the length of packets and so on. So so this is one of the challenges which is going to come with characterizing this complex connectivity types, which are based on combination of the generic connectivity types. So here is an example. So let's say that you would like to consider a system that satisfies massive machine type communication requirement and URLC requirement. So if we have ultra reliable low latency at a massive scale, then in principle, we do not need to define separate ultra reliable low latency, because it's very easy to offer high reliability for very few devices compared to high reliability for a large number of devices, right? So it's not to make this problem trivial. So when does it make sense to combine massive machine type communication and URLC? It does make sense when the information across the devices is correlated. For example, there's an alarm. So here's a model, the information theoretic model that we have used for this. So we have a physical phenomenon, and this physical phenomenon is observed by multiple sensors. So each sensor or each device, IoT device, can transmit its own information. For example, measure temperature, status of the battery, movement sensor, and so on. But it's also simultaneously monitoring a phenomenon, let's say a fire alarm and so on. And then when this phenomenon occurs, then a device may detect it, and if a device detects it, transmits information about that phenomenon. So that means that if the phenomenon occurs, those devices that are detecting the phenomenon are going to send the same type of information. So in absence of the alarm, these devices require MMTC traffic. When the alarm occurs, these devices require URLC traffic, right? So they're supporting URLC traffic. So you can say that the alarm is turning the set of independent IoT devices into multiple antennas that are going to report that alarm. So it seems to me, when I talk about this, it occurred to me that we have seen this similar thing before. And some of you that have been longer in the business could remember that in the 90s, there was a lot of talk about asynchronous transfer mode. So asynchronous transfer mode means that we are defining very small packets, and each type of service is composed by these small packets. So by having the small packets, we can do statistical multiplexing of 4 service types: constant bitrate, variable bitrate, available bitrate, and unspecified bitrate. So this approach of defining generic services and doing statistical multiplexing of them is known, and it has been there since the 90s or even from before. The difference here is that in ATM, the services are multiplexed over reliable optical networks, while the 5G services are multiplexed over a shared spectrum. And that is bringing me to the next topic, which is the spectrum slicing. So if you see the call of the European Commission for projects beyond 5G and the 6G program in Europe, the first requirement was provision of seemingly infinite network capacity that include innovative spectrum use and management. The keyword here is network capacity. Of course, we know that it cannot be infinite. The question is, how do we measure the spectrum capacity when one user wants to have a high rate while another user wants to have a fixed rate, low latency, and high reliability? For example, we have here two users. We have eMBB user and we have a URLC user. And the eMBB user wants broadband connectivity. The URLC wants a fixed rate, very high reliability. So what I'm saying is that characterizing the spectrum only in terms of bits per second per hertz is not good enough, because we are not taking into account the devices which do not care so much about how many bits we are transmitting, but they care to send a limited amount of bits very reliably. So spectrum, to arrive at the spectrum slicing, we are actually borrowing this term from the term of network slicing, where which means that we are sharing the resources while providing heterogeneous guarantees to different services. So we have a couple of years ago, we made this communication theoretic model for the uplink of a 5G system, where we are mixing eMBB, URLC, and MTC. So the challenge there is, do we allocate dedicated spectrum to each service type, or do we allow them to interfere? And the type of results that we would like to show here are the results where, for example, we see how the eMBB data rate is changing as the amount of LMTC arrivals is increasing. So instead of just seeing what is the bit per second per hertz, we would actually like to see what is the trade-off between different types of services. So there are two principal types of spectrum slicing because it's a shared medium. One is orthogonal, where we allocate dedicated frequencies to each type of service, and the other is non-orthogonal, where we allow them to mix and interfere across the frequencies. So having said that, let's look into a toy example of wireless slicing. So let's take a base station where we have a single user that wants data rate, and we have another user that wants low latency and is intermittently active. So so we have the broadband connectivity, which wants continuous transmission. For example, this is the video stream, and the target is to have a high rate. For the other one, we have intermittent transmission, and the target is to have some high reliability under limited latency. So this is taken from a recent book that I published on wireless connectivity, where I have a chapter discussing layering and slicing as two kind of coupled concepts. So let's take the orthogonal slicing case. So this is, again, a very, very simple example. So in orthogonal slicing, we are considering a single frequency channel. So we do not see a allocation of multiple channels. So we are looking into how two services can share a single frequency channel in time. So if it's orthogonal, it means that we are allocating the exclusive time for transmission of broadband and exclusive time for transmission of low latency. The trouble here is that the latency of the low latency user is lower bounded by this L, where in this example L is 4. So if we would like to have lower guaranteed latency for the low latency user, we have to allocate it more often. But if we allocate more often, in the end, there will be no throughput left for the eMBB user. On the other hand, you can also notice that the performance of the two users is totally isolated. So the eMBB user is using all the allocated slots and has a throughput of 3/4, while the URLC user has a latency of L, and this latency is not affected by the activity of eMBB, and the throughput of eMBB is not affected by the activity of URLC. So we can take a different approach. We can say, let's assume non-orthogonal slicing. So this is not necessarily better. It just opens the space for a operational points which are not present in the other one. So here what we are saying is, let's sacrifice some of the throughput of eMBB, and even let's not make it perfectly reliable as it was in the previous figure. On the other hand, we allow the URLC user to transmit whenever the packet arrives. So what we are also doing is that every packet of the broadband user, we are repeating it 3 times in this very simple example. I'm going to show more advanced example later on. And with that, if the collision occurs, for example, here Y1 is colliding with Z1, but Z1 has been encoded before, so we can use successive interference cancellation to recover the packet Y1, right? So with these 3 repetitions, it means that only if 3 consecutive Y packets arrive within the same repetition round, then nothing will be received because of the collision. But otherwise, we can use successive interference cancellation across devices and then satisfy both users. So this is telling that we are reaching an operating point which didn't exist in the previous case with orthogonal access. So the point is that it's not obvious that the spectrum should be divided orthogonally among different service types. They might be actually allowed to share it, and if they're allowed to share it, they might achieve regimes which are achieving better trade-offs of these heterogeneous requirements. So if we look into the spectrum usage, the spectrum regulation is something which happens over a long time. And then based on this spectrum regulation, we can say that we are creating the basic assumptions, the axioms by which we are building wireless systems. Then we are designing the wireless system. And as in 5G, we came up with new models with heterogeneous connectivity. These new models are showing new types of trade-offs from heterogeneity. And hopefully, this is going to change the way we are regulating the spectrum. And we are having new types of allocations in order to satisfy these heterogeneous requirements. So in the same way as there was a intention to work on cognitive radio for dynamic spectrum usage, here is another type of dynamic spectrum usage where we have to satisfy heterogeneous requirements, and they're not necessarily of systems which are competing, but they're actually within the same systems serving, same 5G system serving multiple users. Let's look into the issue of timing. So if we want, I want a simple way to characterize latency and reliability simultaneously is by this latency reliability curve, where we are showing, we're taking a packet of fixed data size, and we would like to see what is the probability that this packet is going to be received at the target destination as the time passes. So this is a non-decreasing function of time, because as the time passes, we can do more things to get the packet received at the other side, for example, retransmissions. But the curve is not exactly CDF because it stops at the residual probability of error. So in the end, there's always some chance that the packet never arrives, right? Because we stop the retransmissions and so on. So the objective is to improve latency and reliability simultaneously, means that the objective is to move from the blue to the red curve. And this can be done by introducing diversity. So introducing diversity in time through coding and retransmission, but this is challenging because we would like to have low latency. We would like to achieve it within a certain small period. Then we can add diversity in terms of frequency. And this is an obvious candidate. So if we want to have high reliability, we allocate extremely large bandwidth. And then in this extremely large bandwidth, we are transmitting many symbols and we're adding redundancy so that we can ensure high reliability. However, bandwidth is expensive and it has to be shared with the other participants. So we're coming to the issue of spectrum slicing that I mentioned before. Then we can actually add many antennas. The trouble with many antennas is that it requires estimation of the channel, proper pre-coding, proper processing, and that is all affecting the latency primarily, but also reliability, because if the protocol for estimating the antennas is not reliable, then we do not have overall reliability of the process. And we can also have diversity through interfaces. So the multi-connectivity paradigm, where we are transmitting data through multiple interfaces. Of course, there the trouble is that these interfaces are not used efficiently if they are used to send the same data. So if we want to compare to the requirements in the traditional requirements in broadband rate-oriented systems, we say that there the objective is to move from the blue to the red curve, because the red curve has a lower average time of packet delivery. That means that if we decrease the average time of packet delivery, we're going to increase the throughput. So in ultra-reliable low latency communication, we would like to move from the blue curve to the red curve, where the red curve is the red curve is meeting a latency and reliability requirement at this point here, at the point where it is crossing the two axes. Then these two actual requirements seem exactly the same. So so why do we differ between them? We do differ because you can also meet the requirements of the second one by using the green curve. So the green curve is telling that you can design your system not to offer very low latency that is not required, but actually to be tuned to offer the latency and reliability exactly at the point where it is needed. So think of, for example, coding theory and introduced by Shannon, or coding for reliable communication introduced by Shannon. The point there is not to use the channel sequentially with the independent transmission of bits. But the point is to group multiple bits, create code word, and transmit the code word. So we do not have the low latency, which is below the length of the code word, but above the length of the code word, we have reliable transmission, right? So that is kind of the philosophy of achieving certain reliability and latency here. So when we speak about low latency, normally we speak about short packets, few symbols, and so on. But let's see what are the trade-offs in a single transmission. So if we fix the latency to T and we fix the data size to D, then the minimal required rate of this link is D divided by T bits per second. Then if we fix the bandwidth, this is going to give 2 times BT channel uses or 2 times BT symbols, such that the rate per channel use is D divided by 2 times BT. So that means that the rate per symbol is the rate per bit, or in bit per second, divided by the bandwidth. So by increasing the bandwidth, we are decreasing the rate requirement on each individual symbol, which is of course understandable. Then we can also fix the energy spent in T. This is, for example, the energy we are using for defining the SNR, the processing, and so on. So by all this, we are fixing what is our channel. And then the finite block length theory can give us what is the maximum reliability that we can achieve. So in principle, out of these 5 elements, you can fix any 4 and find the 5th. So you can say that in ultra reliable low latency, T is fixed, epsilon is fixed, and then we would like to find the other parameters in order to meet these reliability and latency requirements. For example, how much bandwidth and how much power to allocate. But latency is not the only measure of timing. So actually, latency is perhaps the simplest measure of timing, which just says if the packet arrives at a certain layer, so from the moment of arrival until the moment it's delivered, we have a latency of that packet. But if you look into the 3GPP specifications and what people in industrial connectivity are doing, they're actually defining multiple different timings. So there is a end-to-end latency, there is a time of update, there is freshness, there is age of information, there is a peak age of information, and so on. So especially the last one has been taking a lot of attention during the last years, the concept of age of information. So latency performance is historically characterized by packet delays, but there are other timing requirements. For example, if we have tracking applications, like in satellite case, which is this picture is showing, the system is not sensitive to the latency, but it's to the freshness of the last update since the last update has arrived. And we have similar things in industrial connectivity where we do not want maybe the low latency since the packet is generated, but we would like that there is a low pass time since the last time we have observed the state of some physical system. So the age of information was introduced relatively recently, and then there are many of its byproducts that are considered to be better metrics to capture the freshness of information or the timing, let's say, requirement in a certain scenario. The interesting thing is that that here, instead of, for example, in latency, we have that with every arrived packet, which is exogenous arrival, so somebody is generating this packet, and from the moment the packet arrives, we are measuring the latency. On the other hand, we can, in age of information, we can have another type of generating the packets, which is called generate at will. So we actually sample the system and generate a packet, thinking that sampling at this time is most beneficial to get the update to the destination at the right time. So peak age of information is an interesting measure which is showing what is the highest, what is the largest time, or how much outdated the information is when, at the moment when the new information arrives. So it's this vertical line, the length of the vertical line. So how old is the information at the moment when an update arrives? This is important, for example, in control systems where we would like to make decision based on freshest information possible. So it can also be shown in some works that this peak age of information can be related to the stability of the system. Then a case study that our group made with this was in edge computing, where we have a device, for example, IoT device doing edge computing, connected to the base station that is offering edge computing service. So we're having the packets that are queuing at the device. So this is the first queue, and the second queue is the computation queue at the edge, right? So we would like to study, we want to study this peak age of information in a tandem queue. So the interesting thing is that here we are having interaction between the freshness of the information that arrives in the second queue versus the freshness of the information which exits from the edge computing process. So we have shown what is the impact if we have, for example, deterministic computation time versus the case where the computation time is exponentially distributed. Then another interesting measure is proposed by another group is age of incorrect information. So here the intuition is quite clear. So we're saying that we do not care about the old age of the information if the information at the source has not been changed. So if the information is outdated, sorry, if the information is old, but it's not outdated in the sense that the source has not changed its state, so it's actually fine. So this age of incorrect information is only penalizing the age if the state of the source is changing. So this has been also recently published by the group from France. Another new concept that we have considered here in this setup is age of information is in what we call pool-based communication models. So the common communication models that are based on Shannon's model are push-based models. So push-based model means that in Shannon's communication model, the transmitter picks the message, picks the time of transmitting the message, and transmits the message to the receiver. And for some reason, the transmitter always knows that this message is useful to the receiver, and when the receiver wants this message. In pool-based communication, the reading process is different. So in database community, they call Shannon's model, they would call it permanent subscription, meaning that the receiver, whatever comes from the transmitter is relevant and the receiver is subscribed to it. But on the other hand, we have systems where we do not have permanent subscriptions. That is like a satellite system when the update occurs only when the satellite is above the devices, or in query-based IoT systems when the update occurs only when a query is pushed, right? So there's a query pushed to the devices and the devices send an update. So we have actually considered this, and this is a simple example which is showing the setup, which tells that if you know when the queries are going to arrive, if you know that in advance, for example, like in satellite communication, or if it's a query subscription process in database reading, then you can actually optimize your resources to minimize the age of information at the time of query, rather than minimizing the average age of information. And we have shown in this work, which is going to be presented soon at ICC, that there's a quite big difference whether you're optimizing the age with respect to the pull request of the receiver, or you're just doing it as if it's the subscription is permanent. last remark, to come back to the spectrum slicing, because as I said, these are different topics, but I want to connect all of them, is a generalization of the case I have shown before, where EMBB was repeating the packet 3 times. A generalization is an erasure code, where, for example, here we use erasure code 3 out of 5. So the EMBB traffic is transmitted with erasure codes and is sharing a channel non-orthogonally with URLC traffic. So this URLC traffic is going to shoot down some of the packets, but because of the erasure code, actually, we can still recover the EMBB information. And then we have actually considered what are the trade-offs in this single channel spectrum slicing and how they affect the different timing requirements. So without going too much to the details here, is in these 2 graphs, we are showing that if you have latency requirement in the system, then there is a non-trivial impact of the activation probability of the intermittent user to the performance. So we are comparing NOMA and OMA. So if NOMA is performing well, if there is a capture probability, if there is only collision, then orthogonal access is okay. But if we are looking into the peak age of information, then actually as the activation probability per slot is increasing, we have almost constant decrease of the age. And the reason is that we are dropping the packets that have not been transmitted, and we are just taking the newest packet. And the more often the packets are generated, the lower the age, because we have more frequent sampling of the source. So this is just illustrating that spectrum slicing that we have shown in the previous section is really dependent on what is the actual timing requirement in the system that we are observing. So latency, age, and peak age are only instances of a class of some time-related criteria. There is another popular criterion is consecutive errors, for example, which in some way can be related to the age of information. And what we can conclude is that there's a trade-off between good architecture or layering and flexible timing requirements, meaning that the strict layering approach of URLC may not always work. So this is one of the messages of this part. So let's look into the spatial aspects of connectivity, which are being changed as we are moving towards 6G. So since 5G, it became a technology trend to use antennas with many elements, like in massive MIMO, large intelligent surfaces, and reconfigurable intelligent surfaces. So so the question is, how can we use these many antennas to satisfy the 3 types of connectivity which have been defined by 5G? So if we look into the use of massive MIMO and IoT, the pros are that we have, especially ultra-reliable low-latency communication. The pros are that there are very high SNR links, which are quasi-deterministic, and they offer extreme spatial multiplexing capability. However, the cons are that the channel acquisition procedure is very expensive, and that there are additional protocol steps. So it might not satisfy the low latency requirement. That's why we have to be creative. If we use, for example, massive MIMO, let's say industrial low latency connectivity, and instead of estimating the channels every time, we can use some predefined spatial channels through which we are transmitting data from the machines. Then one of the topics where there's tons of paper being published every day is the topic of reconfigurable intelligent surfaces, where we have base station and the reconfigurable surfaces is part of the wireless environment, and that can affect the wireless signals from the devices which are going to the base station. So simple IoT devices can significantly benefit from the favorable and reconfigurable wireless environment offered by this reconfigurable intelligent surface. So we have actually had a case study in a satellite communication where we are deploying a RIS next to an IoT device, and we are using the predictive satellite mobility to adjust the reflective surface. So you can think that the coefficients of the reflective surface are adjusted to track the satellite. And we have shown in this recently accepted work that we can define a multi-objective optimization problem where we can change the coefficients with this, as I said, predictable mobility of the satellite to, for example, compensate for the Doppler spread, compensate for delay spread, or maximize the received power from a device in an uplink transmission. Then another, I think this is even more interesting possibility, which is arising from the reconfigurable intelligent surfaces. Imagine that each reconfigurable surface changes the reflection coefficient sinusoidally according to some frequency. So what will happen is that the RIS is starting to act as a mixer, frequency mixer. So there's a signal between the two devices here, where the signal, which is the direct signal, comes at the frequency FC, but the reflected signal is mixed with some frequency FR. So it comes at two different frequencies, FC minus FR and FC plus FR. Why would we do this? I mean, why would we allow the wireless environment to change the spectrum? Well, there could be interesting uses of it. For example, if you have multiple reconfigurable surfaces and each of them has its own frequency, then by looking at the frequency of the reflected waves, we can identify from which paths they're coming. So instead of identifying the paths in time as is usual, here we can identify them in frequency. And this is also work actually accepted yesterday on nonlinear wireless propagation. So let me look into the final part, which is the blockchains. Nizar, I think I will make it into 45 minutes, so it should be okay.
Perfect. Thank you.
Because we started a bit later. Sorry. So in massive IoT systems, the interactions among the devices were envisioned to be mostly based on uplink transmissions. So, for example, this is the assumption in many mainstream systems like LoRa and Sigfox, where we have uplink transmissions, sporadic transmissions from many devices. However, there are at least two drivers to change this pattern of interaction. One is smart contracts and blockchains, which I'm going to talk about now. And second is distributed learning, because if we want to have distributed learning and transfer some knowledge towards the devices, then we need to have two-way communication between the IoT devices and the base stations. So what is a distributed ledger? Distributed ledger is a more general concept than a blockchain. Let's say blockchain is a specific type of distributed ledger. Ideally, it's a truthful, immutable account of the history of transactions. For example, there is a nodes connected in a network, and this network knows perfectly what have been the transactions done within the network, so that if I transfer $2 to Nizar, and then I inform everybody else that I've transferred him $2, so I cannot transfer the same $2 to somebody else because they have been already spent. So that was the main idea of distributed ledgers, solving the double spending problem. The actual distributed ledger is an approximation of the ideal due to the non-zero delay of writing in databases. So in order to write to these databases, to distributed ledgers, we need to have a consensus which is supported by a highly non-trivial acquisition of the right to create an update. So for example, you cannot make a payment unless you prove that you have done something to write this in a ledger. So that's what is the now infamous proof of work in blockchain, because it's spending a lot of energy. But more interesting capability of the distributed ledgers is in the smart contracts, where smart contracts is modifying the state of a database, and this modification is informed to everybody else. For example, let's say that I'm measuring some pollution, and when I register a value of pollution, I can inform everybody else in the network so that I cannot change the value afterwards. So, and blockchain is a specific instance of distributed ledger with linear chain structure. And the objective is to have finalized transactions. So to have transactions which are accepted and will not be reverted with high probability. So if I do the payment, this payment is final and it's not going to be reverted with a very high probability. So a smart contract is a digital contract that combines programs, computer functions, and logic for legal documents. For example, this is the renting of a bike smart contract. Why it is important for IoT? Because there will be, we envision that there will be many autonomous transactions among IoT devices, buying and selling of data, verifying of data of the other devices, and so on. And this cannot happen with, let's say, human level verification. So there has to be a distributed way to verify these contracts among different devices. For example, in a smart contract, an IoT device says if the temperature is above certain level, then you have to turn off the machine. And then if there is an accident happening, then you can actually go back and see who failed into doing this, into fulfilling this smart contract. Right? So why should we care about the communication community? Why should the community, our community, care about this? Because there are many controversies why people would use blockchain, but whatever will be the use of blockchain, there will be a lot of communication. And in California Gold Rush, if the story says that people that went to find gold maybe got rich, but the people that got rich for sure were people making shovels, right? So in principle, the role of communication engineers here is to make shovels. And how do we fit this DLT to the IoT devices defined by IoT services defined by 5G, MMTC, and URLC? Well, the capabilities and requirements of MMTC and URLC are quite different. The challenge in MMTC is the computational requirement. So these are small devices that cannot really participate in a distributed ledger. So they have to participate in a simple variant of a distributed ledger. And then the challenge in URLC is the transaction finalization delay. So for example, how do we measure the latency? Do we measure it based on a single transmission, or do we measure until all devices confirm this transaction, right? So what we have tried to do in a relatively simple and experimental work is we took some blockchains which are popular, like Ethereum, Bitcoin, Fabric, and also one distributed ledger called IOTA, which is not a blockchain, it has a different structure. And then we have tried to see what is the latency of validating this through LoRaWAN, through a very established IoT system. So it turned out that Bitcoin had relatively low latency, but IOTA, for example, which is intended for IoT, had a very large latency. And the reason for this is the limited capability of LoRa to do two-way communication, and also the way in which the transactions are packed, what is their length, how they are emitted, and so on. So this is just telling that we need to have cross-layer optimization of the distributed ledgers and the underlying technology. Otherwise, the latency can become unbearable. We see here that we have more than 100 minutes of latency. So a useful application, which we also was confirmed to our group from some authorities, is the application of blockchains and IoT for distributed pollution monitoring. So we have made experimental setup in the lab where we are with NB-IoT, where we are showing how much traffic there needs to be in order to have verified pollution measurements. And why this is important? Because if we have a functioning system for measuring, for example, of CO2, then we can make a carbon emission trading system which is completely automated based on the IoT devices that are interacting among themselves. And a more futuristic concept is a general data market and protocols for trading between IoT devices. And we have actually, in a recent paper, we have made a framework for designing data markets for IoT devices. And we have tried to make a benchmark what is the requirements in terms of uplink and downlink, and also energy consumption for supporting these market transactions. So this brings me to the end, that I've talked about interaction among very different generic traffic types, and how do we compose services by combining these traffic types. Heterogeneity is redefining the spectrum usage, and we need a better and new understanding of the timing requirements, which can also be coupled to how are we slicing the spectrum, discussed in the previous point. There are new opportunities in spatial processing, especially with these reconfigurable intelligent surfaces. And finally, distributed ledgers may fundamentally change the interaction and traffic patterns in massive IoT. So that finishes my talk. Thank you very much for your attention.
Thank you very much for the really nice and well-presented presentation. Really interesting. So time for questions. We have some questions on the chat. The first one by Abdul Hamid Taha. He says that 4G, 4G had different bearers for the different types of delay, and he asking that this could be, let's say, expanded to 5G. So will 5G also have this, and what about 6G? So as a way to differentiate between the delays among the different applications.
I mean, this is a good one, because I think there will be in the end different classes of latency that are going to be defined, and these different classes of latency are going to have interaction with the other parts of the latency budget. For example, the computing or compression and so on. So we will need to have bearers that are capable to negotiate different latency requirements depending on what the end node is doing. So I don't think that it's feasible to have always 1 millisecond requirement. We need to define interfaces to have the scalable requirements for beyond 5G, let's say. 6G, I don't know much about it, and I don't know whether somebody knows much about it, but I think we will have a redefined timing requirements, not only in terms of latency, in terms of a number 1, 2, 5, or 20 milliseconds, but also in terms of how is this timing measured. For example, that's why I've been showing this peak of age of information, and so on. So whether it's the timing is measured per link, whether it's measured per consensus, like in distributed learning or in blockchain and so on. So I think in 6G, latency is going to be generalized to multiple timing measures. That would be my guess.
Yeah. We will see what will happen in 6G. Another question by Abdul Hamid. He is asking about the RISs. Okay, so he is asking how autonomous do you think that the RIS management will eventually be, and does this involve introducing considerable intelligence processing at the physical layer?
Yeah. So the important point for IRS is, first of all, how it is going to be controlled. What is going to be controlled through a out-of-band channel? For example, you're putting a channel through a fiber or through a dedicated wireless system, or is going to control through the same channel it is controlling. For example, you're using the same wireless system that is being affected by the RIS in order to configure the RIS. And they are considered to be nearly passive at the moment, which means they are not radiating, but there will be a lot of computational complexity to, if we would like to, for example, have steering of beams for multiple users or multiple systems. We're having a EU project now where we would like to show how we can have the same RIS in the environment used by multiple operators. And in that case, the RIS, of course, has to have some intelligence, not only to reconfigure, but also intelligence for accounting, how it helps different operators, right? So I think what is the next step for RIS is one of the important next steps. There are many next steps, but one of the important is to define a proper protocol architecture, how it is going to be controlled and how it's going to be integrated into a cellular system.
Yeah, especially because it can generate more interference than benefits, actually.
Yeah, in principle,
okay.
yes.
Yeah. Okay, good. So one more question is related to the delay in blockchain. So the presented results for delay are the communication delay. We understood, right? So it is not the delay from the operation itself, and if it is proof of stake or proof of work and so on, right?
Yeah, exactly. So these are the delays the delay I was presenting, in the blockchain part is the full accepted transaction. That's why it was very long, 80 minutes. But the delay I was presenting for the 5G part was just for a single transmission. And when we talk about timing, we're actually preparing a paper on timing for wireless system, because we're trying to define a framework to capture all these different types of timing, from a single link, multiple link, consensus, and so on.
Okay, very good. And one last question, maybe timely now for artificial intelligence. Do you think that artificial intelligence can help into detecting what is the requirement for delay for every one of the applications? Because usually it is a dynamic scenario, okay? And to know exactly what is the requirement for everyone is difficult. So do you think that AI can help in such an optimization?
I think AI can always help if the model is difficult or if the algorithm is too complex. So,
and the model is difficult here whenever we have so many applications running at the same time.
Yes, that's why I mentioned, for example, we have multiple applications, composite applications. The role of AI, the machine learning, will be to discover correlations and kind of predictably allocate resources to meet various timing requirements. That's what I mentioned already at the beginning. So I think AI would be, or machine learning would be very helpful into dealing with composite connections, which are having, for example, partially MMTC, partially MBB, partially ULC.
Yeah, because of the mix, and it is not always a fixed mix.
Exactly. That's
okay, good. So thank you. More questions from the audience. You can unmute your mic if you want, and if you have a question. Questions from audience? Nothing. Okay, then we come to the conclusion. Professor Popovski, thank you again for your time and for the very nice presentation, very insightful. And we will be posting the recording on our website if more people want to listen to it, and eventually contact you if they have any further questions.
Thank you. Thank you very much for the invitation. It was a pleasure to talk to you.
Thank you all for being here. It has been a pleasure to have you on this CSIM seminar, and looking forward having you in more seminars in the future. Thank you all, and thank you very much to the ComSoc team for hosting and arranging for the seminar. Lorian, thank you very much.
Thank you.
Thank you all.
Bye.
Okay. Bye.
Bye.